Okay, I'm now sharing my screen. Okay, week 0. Let's directly look at the assignment solutions.
May I mail you the whole assignment solution? I have told.
No, that's okay. I mean, no need to waste time. Yeah. So, which questions?
First question.
Okay. So, what do we have here? Let me just check if the one second. I started recording, right? Okay, cool. So juggler is going for show, looking for red balls among his bags were different. Okay, he found 80% of the bags contain 10 red balls, 10% contain 15, 5% contain 3, and 3% contain 1, 2. Okay, fine. What is the mean? So mean and expectation are synonymous, that you understand? Okay. Now, what is the formula for expectation? E of x is a random variable, is summation over x times p of x.
Yes, sir.
That formula you know, okay?
Yes, sir.
Now, we are given various p values. These are all probabilities, right?
Yeah.
Because they add up to 100. 80 plus 10 is 90, 95 plus 3 is 98, and plus 2 is 100. So these are probabilities. And you have the x, so you have the count as well for each probability. So you can apply the formula.
Acha, yeah, E of x equal to summation of x into px. Simple, na?
Yes.
Okay, finish. I'll do it next.
Okay. So that's why the hint is given number of red balls, which is x times the probability. That summation.
Fine, I'll do it.
Okay.
Next, third question.
Okay. Second one was difficult. Okay. But third, okay. So in third, okay, so this is a bit interesting. So this is a property of the Poisson distribution. So
mean and median is same.
Mean and median is same, is it? Oh, that I don't know. For Gaussian, mean and median is same. For Poisson, I am not sure. I think so. Okay, okay. It may not be the same because the answer here is this. But okay, let's see how to solve this. Okay, so let's first think of median. Okay, so median में, so what we do is, okay, so the formula for Poisson is lambda to the power x, e to the power minus lambda by x factorial, right?
Okay, lambda to the power of x into
E to the power minus lambda by x factorial.
By x. Yes.
Okay, this is p of x, right? Right?
Yes.
Okay. So now what you can do is you can keep substituting x. So what is x equals to 1, x equals to 2, x equals to 3? What do you get? So for x equals to 1, you will get lambda times
e to the power minus lambda.
e to the power minus lambda, right? So then for x equals to 2, you will also get lambda. So here you can also put the value of 3. So for this specific distribution, lambda is 3. So for x equals to 0, you will get e to the power minus 3, right?
Yes, sir.
Can you confirm?
Yeah, yes, sir.
Okay. For x equals to 1, you will get 3 e to the power minus 3, right?
3 e to the power minus 3.
Right? For x equals to 2, what will you get?
Yeah, it's equal to lambda 3 square 9 into e to the power of minus 3 e to the power minus 3 upon lambda upon 2 factorial.
Right. So yeah, so you did it. So 3 square into e to the power minus 3 by 2 factorial, right?
Okay.
For x equals to 3, you are getting again 3 square e to the power minus 3 by 3 factorial, right?
Yes.
So are you writing these values down?
Yes, no, sir. Let me write it.
Oh, it's important to write it down so that you can visualize it.
3 into e to the power of
so the first one was e to the power minus 3, simple, right?
Okay. It is
The second one is 3 e to the power minus 3,
3 to the power minus 3.
right?
Hmm.
The third one is 3 by 2 e to the power minus 3, I think, right?
3 by 2 into the power minus 3.
Come-
ठीक है, तो-
Just confirm once.
No, it's fine.
Okay.
3 to the power minus 3. 3 e to the power minus 3. 3 by 2 e to the power minus 3.
Now here's your task. So what is x equals to 3? So what value do we get for x equal to 3?
X equal to 3 given x equal to 3 by 2 into the power minus 3.
Exact as x equal to 2, right?
Yes, sir.
Okay. Now x equals to 4, what do you get? This is the last one, I promise. X equals to 4.
X equal to 4 to the power 4, 81.
Mhm.
To the power minus 3 upon x equal to 4. 4 factors, which is equal to 24. 24. 81 into the power minus 3 upon 24.
And upon 24, right?
Yeah.
So as you will see, the maximum, so if you remember the definition of the mode, that is the highest point in the series, like the maximum value, that thing, right? So as you keep increasing the x, the value will keep decreasing beyond 3. So 2 and 3 have exactly the same value, which is 3 by 2 e to the power minus 3, right?
Okay.
So that is why both 2 and 3 are the mode. So you just have to see the trend of the distribution, how the Poisson distribution look. It starts from 0, it increases slightly, it peaks around 2 and 3, and then it keeps falling as x goes very high.
Understood.
Right.
Okay. Yes, sir. Question number 5. Sir.
Okay. So this is not a general question. This was since it's week 0, it's a specific math question about visualizing things.
I know, sir.
Okay.
But I didn't know that I have to do it that way. X equal to 1, x equal to 2.
Mhm. Okay. Okay. So what is this? X is experiment consisting of n equals to 20 trials with success probability 0.3 is modeled as a binomial distribution. Okay. So this is formula, right? So can you tell me the formula for binomial distribution?
Binomial distribution.
So what is P n comma k? Let's say there are n trials and k success.
NCK, I'm telling the formula. NCK into p to the power of k into 2 to the power of n into 1 minus p to the power of n minus k.
Perfect. So here n is given as 20, right?
Yes, sir.
And p is given as 0.3.
Yes, sir.
Right? Now you have to find the probability for a specific value of k, right?
Yes.
That the random variable equals its expected value. So what is the value of k? The k is the expected value. Now, do you know the formula for expectation of a binomial distribution?
P to 1 minus p.
Yes. No. Yeah. Okay. No, it is np.
Okay, NP, yes, sir, NP.
P1 minus p is not right. np.
No, that is the principle.
So what is the value of np here?
P into NP.
No, not p into np, just np.
N.
Okay.
N is how much, sir? Obviously, N is 20
Huh.
and P is 0.6.
Yeah.
Yeah, but it is 6.
6. So it's basically the question is asking. So you know that for this distribution, the expected value is 6. So what is the probability for x equals to, so k equals to 6,
But K equal to 6, sir.
right?
Yes, sir.
So the last line means that it's telling you that the random variable equals expected value. You know the expected value from the formula, which is 6.
Yes.
So random variable here is k, right? Because the number of trials is fixed, the probability is also fixed. What
Yes, sir.
changes is the value of k.
K, yes.
So that's the random variable. So k equals to 6 may, what is the expected, what is the probability? So now we have to put it in the formula.
Okay. 20C6.
Yeah. 20C6 times 0.3 to the power 6 and 1 minus 0.3 to the power 20 minus 6.
1 minus. Acha, 0.7.
Yeah, 0.7 to the power 14.
14.
So if you solve it using a calculator painfully, then you will get it.
Okay.
Okay.
Okay, I'll do it, sir.
You will get around 0.19164. I actually wrote a code to check. Anyway.
Okay. Please.
Yeah. Okay, what's next?
Next is the rank elements.
DSA, you had something, na? I remember seeing in our notes.
Then graph theorem linear algebra for participants.
Okay.
Data structure में कुछ नहीं है, algorithm. Graph theorem linear algebra.
Okay.
Questions from 1 to 3, 4. Okay.
Every real matrix always has eigenvalue decomposition. True or false? False. Okay. So why? Eigenvalues.
Yes, I know, eigenvector and then eigenvalue.
Yeah, but can eigenvalues decomposition be done for any matrix? That's the question.
Yes,
that is not right.
Can be done.
No.
The singular value decomposition will do not.
Exactly. So singular value decomposition exists in practice because eigenvalue decomposition cannot be applied everywhere.
Achha.
Singular value SVD can be done to any matrix. It can be a rectangular matrix. But eigenvalue, have you ever seen being applied to a rectangular matrix? It cannot be done.
No, it's a square matrix.
Exactly. So that's the question. That eigenvalue, any real matrix includes square matrices as well as rectangular matrices.
Okay.
But EVD cannot be applied to rectangle.
Okay, fine. Okay,
Right.
clear. The next question
Oh,
is second question.
2, right?
Uh,
Oh,
But I
this
don't know
is
what
this is not even a question. Wait. Oh,
I
I
know.
think you misunderstood. So adjacency matrix, you know, okay?
yes,
Okay.
ABCD,
So,
ABCD,
हाँ,
A to
so
A, 0 हो जाते हैं.
exactly.
A to
So
B,
the row IDs and the column IDs are nodes of the graph, and edges are the values in the matrix, right? So what are the so 0, 0, 1, 1, 2, 2, these are the diagonal elements of any
Yes.
matrix.
Yes, yes.
So what would that edge indicate? 0, 0?
0, 0 means A to A.
Yeah. So self loop.
Self loop, no self loop, sir.
Huh.
It's said.
So no self loops is set. That means what that entry to 0, 0 should be?
Means apart from 0, anything could be there.
No. So okay. So a non-zero value in the adjacency matrix that denotes existence of an edge, right? Do you agree?
Yes, yes, yes.
So when the edge does not exist, then what should the value be?
0.
Exactly. So यहाँ पे they have said that no self loops. That means A, B, B, that thing does not occur.
Okay.
That means none of the diagonals can have any edge in it, which means 0 should be there.
Yes.
Okay.
What is the sum of the entries in a column and next question?
Okay. Let me remember what an incidence matrix is. Acha, okay. Those is sum of entries. Huh, okay, got it. So do you remember what an incidence matrix is?
Incidence matrix.
Mhm.
Incidence matrix means
So
a graph होगा, graph is there, ठीक है?
Hmm.
So using the graph, I'm going to create a matrix and that do not have any direction. The graph that do not have direction. इसकी जो हम ये बनाएंगे,
no, that is undirected graph you're telling. What is a so okay, for any graph, you know how to construct the adjacency matrix, right? The rows are nodes, the columns are nodes. Okay. So incidence matrix is another way of representing graphs. Any graph, it can be directed, undirected, whatever.
I understood. I remember.
So incidence matrix में the rows are nodes and the columns are edges.
The rows are nodes.
Yeah. So try to draw it a bit if you are remembering it after a long time. So if you have a square matrix, let's say.
Rows, nodes.
The row 1 is node 1, row 2 is node 2, and so on. So the rows are indicating nodes.
Row 1 is node 1.
Yeah. So we are starting counting from 1, let's say. So the first row is node 1. So what happens in adjacency matrix? The first row is node 1, second row is node 2, but the first column is also node 1, the second column is also node 2. And then the entries are row, column, which is the edge between node 1, node of the row, node of the column, right? That's the adjacency matrix.
Yes.
In incidence matrix, the only difference is the rows are same as before, but the columns are edges. Okay.
Yes, sir.
Right?
Yes, sir.
So now, if you, let's say you take node 1, okay.
Yes, sir.
Now you have let's say the graph has 10 edges and 3 of them are incident on node 1. So 3 of the 10 edges in the graph start from node 1, let's say. Okay. So that means in that row corresponding to node 1, which is row 1, there will be 3 ones somewhere. Clear till now? So basically my incidence matrix is telling that for each node, which of the edges are related to this node, let's say. It's the proper term is incident on this node. So that's why incidence matrix. So basically, if my node 1 has 3 edges starting from it, then 3 of those columns will be 1. Column entries will be 1. Right? Similarly, for node 2, it will be some, however many are starting for it. So can you tell me how many? Okay. So this is the row view. Now, if you consider any column,
Yes.
each column represents what?
What is it?
Each column represents what?
Vertex. One vertex.
No, vertex is the same as node.
The one edge.
Edge, exactly. Each column is an edge. So in the entire column, so how many nodes can an edge be related to?
Yeah, it can be two, sir.
Two endpoints, right? So the proper term is incident upon. So the proper terminology is how many nodes an edge can be incident upon or basically related to. That is 2 because it has 2 endpoints. Therefore, each column can have at most 1 in 2 rows, right? The starting and the end. And that's it. That's the answer.
Okay.
Right. So you just have to visualize the incidence matrix.
How the question is not easy. I'm not understanding.
No, so yeah, so basically here if you drew the incidence matrix for any graph, so let's say you take a 3 or 4 node small graph and you draw the incidence matrix for it, then it would have been extremely clear to you.
Yes, sir, yes.
That's the trick to these things.
Then the last question, sir.
Fifth or sixth?
Fifth, sir.
Fifth, okay. Okay, so what is this? For a d-dimensional identity matrix, trace equals.
No, sir.
Okay.
It's the last question of this year. Last question. Please go to the last question. Which is the ordinary.
Okay. I see this one.
Yeah.
Okay, so this seems to be a larger question. Let's see. A random variable x minus 2 by 4 has mean 0 and variance 1. Okay. What is the mean and variance of x? So you will do a little bit of algebra, but I think you can do it on your own. Let me help you along. So let's say some x minus 2 by 4 is a random variable, right? So let's for ease assign it to some variable y. Okay, y. Okay.
Yes, sir.
So y equals to x minus 2 by 4. Now you are writing these down, right?
Yes.
Okay. So let's assume that y equals to x minus 2 by 4. Now what is being told in the question? It has mean 0. That means expectation of y is 0, right? Ey is 0 and it has variance 1. So variance of y is equal to 1. Okay. Now it is asking you the expectation of x. E of x, that's the question, right? What is the mean of x? So E of x equals to E of what? So how can you express E in terms of y? Can you do the algebra?
Yes, sir. E of x plus y equals E of x plus E of y.
No, you are telling me a formula. That's not what I'm asking you. You are telling me the linearity of expectation formula, I think.
Yes, sir.
No. You have y equals to x minus 2 by 4, right?
Yes, sir.
So how can you express x in terms of y?
Sure. Yeah, I am going to put substitute the value of y in E of y, and I will solve it.
In E of x. So, sorry. Yeah. So first tell me, let's quickly do this. It will take a minute. E of x equals to what? So x equals to what in terms of y?
Yes.
What is it?
X equal to 4y plus 2.
Exactly, perfect. So E of x equals to E of 4y plus 2 that you have just calculated, right?
Yes, sir.
Now you can use linearity of expectation.
E of x equal to 4 into E of y. E of y. And E of 2 is only 2.
Yes.
So 4 into E of y is 0. So 2 is the answer.
2 is the answer. So first 2 you have already got. Okay. Similarly for variance, how will you do? Variance of x equals to variance of 4y plus 2.
Yes, sir. Variance of x equal to?
Again, like Ex equals to E of 4y plus 2. Now variance of x equals to variance of
4 16 हो जाएगा. 4 square. Variance of y is 1.
Variance of y is 1. So yeah, so basically the 4 will become 4 square, so 16.
Okay, clear हो जाता.
Okay. Right.
सर थोड़ा बेसिक क्वेश्चन पता नहीं कैसे थोड़ा सा रुक जा रहे.
No, it's fine. These are the ones that I can help with the most. Okay.
Yes, then sir, week 2, week 1.
Okay. Sec. Sorry, I clicked on the wrong link. I have to go to the assignment solution 1 and 2. Week 1.
Yes, sir. Question number 5.
Oh, the lot of the solution has already been given. Okay.
I didn't understand.
So joint probability density function for R and S is given by f of Rs and whatever this thing. And R is between 0 and 1, S is between 0 and 2. So first things first. So let's say we believe this. Okay, so let's say we believe this. This we will come to later.
No, sir. First part only, first line only I am not believing.
No. So let me just confirm what you need to understand. So
sir,
if
one thing. यहाँ पे condition super में देखिए question में. आप देखिए 0 less than R less than 1, okay? And 0 less than S less than 2. So somehow I can assume that S is greater than R.
No. So S can be greater than R, but it's asking you to limit yourself to the cases where R is greater than S.
Okay.
Right. That's the question, right?
Okay.
So S can be greater than R, that I agree, but it wants question wants you to compute the probability in the areas where R is greater than S, right? So that's why this condition is being imposed on the, so double integral you understand because there are two aspects, ds and dr. So this thing is naturally followed from the question, right?
Fine.
Because the question is asking it. This part is a bit tricky, but before we dive into this, if we believe this, then is the rest of the part clear?
Sir, calculation I know.
Calculus part is clear, right? Okay. So why is this coming out? Okay. So here your R, so by default, all these values are from minus infinity to infinity, right? By default, whenever you take integral over a continuous probability density function, then you consider from minus infinity to infinity. Now here it has been mentioned that R lies between 0, 1 and S lies between 0, 2. So you don't need to go from minus infinity to infinity, right?
Yes.
So that's why you see here, by default, they had minus infinity to infinity for R. The outer integral is for this R, right?
Yes.
So by default, they had minus infinity to infinity. But here they replace it by 0 to 1 because the question tells you that R is always lying between 0 to 1. You do not need to look beyond that. Okay?
Yes.
Now here, you are interested in all the cases where R is greater than S.
Yes.
Right?
Yes.
So R is the upper bound on S. S cannot take any value beyond R.
Yes.
Right? So whatever S happens, whatever the integral of S has is there, that cannot go beyond R.
Yes.
Are you convinced? According to the question, So
Okay.
S cannot
Okay,
go
understood.
beyond R,
Understood.
therefore the upper, okay. So it's minus infinity to R, that is convincing. And again,
Yes.
because the question tells you that S is always greater than 0, so it is 0
Done,
to 1.
done, done. Okay, खत्म हो गया, चलिए.
Okay.
6.
Sixth the formula is given, so this will be quick. So suppose there are 3 coins, out of which 1 is fair, 2 is biased, 1 coin uniformly at random. So what is the probability of picking 1 coin uniformly at random? 1 by 3, right?
Yes.
If there are 3 coins and I'm randomly choosing uniformly 1 coin, it's 1/3 probability of selecting any of those coins. And then given any of those coins, I will. So this is where the 1/3 is coming from. Okay.
That I understood.
Okay.
That got it.
And then I am flipping it 3 times. So probability of heads is given
0.1.
for the 3 coins. Okay.
Yes.
And the event is given HTT, heads, tails, tails. So if I randomly choose the first coin, what is the probability of HTT? It is?
Yeah, this is 1 by 3 and TT is 2 by 3. Achha, given, the value is given 0.6.
Right. So 0.6 into 0.4 into 0.4.
Yes, sir.
Right?
Yes, sir.
Okay. So this is that number that we just came up with.
Okay.
Right? 0.6 into 0.4 into 0.4 for the first coin. Okay.
Yes, sir.
For the second coin, it is 0.1 into 0.9 into 0.9, right?
Okay.
What if for the third coin, it is 0.5 into 0.5 into 0.5,
Okay.
which is 1 by 2 half into half to the power 3, which is 1 by 8. Right. So you pick any of these 3 coins at random at 1/3 probability each, and given each of those coins, you have this much probability of getting HTT. So this is the formula. If you solve it, you will get.
Clear. Okay. The next question is 7.
Okay. So, right. This is an interesting question. Among a stock of 6 capacitors, 2 are known to be defective. So I have 6 items, 2 are bad. Testing one at a time until the damaged and defective ones are found. Let us denote M1 as the number of tests until the first damaged one is found, M2 as the number of tests until the second damaged one is found. What is the joint probability mass function of M1 and M2? Let me think of it. So the key idea is let us so basically you have 6 capacitors lined up one after the another, and then you're checking them one after the other, right? So M1 is the number of checks before you find the first one, and M2, which is crucial, is the number of additional checks. Number of additional checks, right? So let's say the third capacitor is faulty. So you check 1, 2, and then at 3, at M1 equal to 3, you find the first bad one. And then let's say the fifth capacitor is faulty. So you again start counting from 1 and 2. So M4 is 1 and M5 is 2. And at M2 equals to 2, you find the second bad one. Are you getting it? So this number of additional tests is important. Okay. So again, let's see. Let's say you have 6 capacitors and the third and the fifth one are bad, right? Let's say that's the sequence. So what would the value of M1 and M2 be? 3, 2.
Yes.
Why? Because you check first, you check second, you check third, and then you get the first bad one. First damaged one is identified after 3 M1 checks. Sorry, M1 equals to 3 checks. And then how many additional tests? Additional tests is what? 4 and 5. Two additional tests. So you have, so this is the M1 and the M2. So basically, how many values of M1 and M2 can be there? the values of M1 and M2 depend on the position of the bad capacitors, right?
Yeah.
So there are 6 bad capacitors. If you randomly point out any 2 of those locations, then you can uniquely specify M1 and M2, right?
Yes,
Are you convinced about this?
yes. Yes.
Okay. So the problem becomes, how many ways can you uniquely specify? So how many ways can you randomly put those 2 points?
Sir, 62 तो मुझे clear है, ठीक है?
6C2, okay.
हाँ, वो तो clear है। आप 1 upon क्यों कर दे रहे हो?
1 upon is the probability, 6C2 is the count. So 6C2 is what? 62 is the number of ways you can identify 2 bad capacitors among 6, right?
That I understand.
So if you are considering uniform randomness, then 1 by 62 is the probability of any one of them. Got it? I mean, if there are 100 events, if there are 100 variations of an event and all of them are equally likely, then what is the probability of any one of them occurring? That is 1 by 100.
No.
Right? Similar to this. Or if you have a uniform distribution, okay, so let me make it more mathematical. If you have a uniform distribution and the span of the uniform distribution is given, right?
Yes.
Which is what? Let's say the uniform distribution lies between 1 and 10. That is specified to you.
Fine.
Then what is the probability height? What is the height of the uniform distribution? That will be 1 by that span. Yeah. So that's same logic.
अच्छा, तो ठीक है, समझ आ गया, clear है।
Okay.
Actually 62 तो मुझे clear हो गया, वो कैसे और हमारा number of ways।
Oh, I see.
But just saying what that was I was।
Oh, I found the 62 thing more challenging to reason out because of the number of additional tests thing. Okay. Fine. Okay, got it.
Okay. Then sir, 5, 6, 7 okay. Linear algebra, fourth question. Linear algebra.
Let's see if I'm able to answer this. Oh no, it's the solution is given. So H is a n cross n symmetry.
Sir, मुझे पूरा clear है। आप पढ़ लो एक बार।
Okay.
छोटा सा question।
H, no, you have a doubt in this, right?
Small doubt, small.
Okay. So if H is a n cross n symmetric matrix that is equated to I minus 2u u transpose, where u is unit vector Rn, u transpose is 1. One of the eigenvalues is u, eigenvectors is u. Okay, fine. So what is the doubt?
Doubt is sir, H equal to ये तो मुझे समझ में आता है। I minus 2 into u into u transpose।
Yes.
मैंने u को multiply किया। तो कैलकुलेशन करने के लिए u transpose u लाने के लिए क्या?
नहीं, so what is the eigenvalue eigenvector formula? HU equals to lambda u, right?
Yes, sir.
Since u is the eigenvector, if we multiply h with u, that will give us lambda u, and they are asking what is the value of lambda.
Okay.
Right?
Yes.
So let's try to solve this orally, maybe, or you write it down. So h is I minus 2u u transpose, right? Times u.
Understood. H equal to this. अब मैंने u इसलिए मल्टीप्लाई किया, आप u को अंदर डालिए। I equal to 1 है ना? I equal to 1 unit matrix।
Yes.
Now u को मल्टीप्लाई जब करें तो u हो गया।
Perfect.
Minus 2u u transpose u। u transpose u is equal to 1।
Perfect.
हाँ, तो u minus 2 equal to minus 2।
Perfect.
So ये u इसीलिए मल्टीप्लाई किया so that I can apply this formula ना, u transpose u equal to 1।
No, इसलिए multiply नहीं किया. That's a happy accident. Or not accident, that's how the question was decided. Multiply इसलिए किया because HU equals to lambda u. That's the eigenvalue eigenvector formula. So how do you, given any matrix, how do you identify the eigenvector and the eigenvalues? So eigenvector is such a vector, if you multiply it with the matrix, so if the matrix is H and the eigenvector is, let's say, X, not U, okay? So Hx will be some constant times X. That's the definition of eigenvector and eigenvalue, right?
Yes, sir.
So यहाँ पे X is specified as U. So HU will be some constant times U.
Okay.
Right. So HU we are not multiplying because U transpose U becomes 1. That's the algebra. That's separate. The reason for doing it is that gives us the eigenvector and the eigenvalue.
Okay.
So here the constant is -1.
Yes,
right.
Sir. Okay. Clear.
Okay.
Next question is machine learning.
Okay. Question?
235. Machine
Oh,
learning and optimization.
235. Okay, 2.
Yes, sir.
So what is to consider x1, x2 as some IID samples from a Gaussian distribution with sigma greater than 0. Let the mean be this. Which one is this? Which one is true?
Yes, sir. सर ये भी सब ठीक है, क्लियर है, सारे
Okay.
बातें मुझे क्लियर हो गई, ठीक है।
Okay.
अब प्रॉब्लम ये है, ये देखो आप आंसर हो जाए xi minus mu का होल स्क्वायर, ओके, इक्वल टू I इक्वल टू 1 to m xi minus mu m plus mu m minus mu, ये भी समझ में आता है, ठीक है, होल स्क्वायर, ये भी क्लियर है। mu m को डाला गया है, ठीक है, minus mu m plus mu m equal to 0, okay, then I'm going to get the first equation again, okay sir. Now what is they are doing? Xi minus mu m whole square, how they are doing this? So this is whole square ना, xi minus mu m का plus mu m minus mu का whole square। अब इन्होंने क्या किया, मतलब ये हुआ a plus b का whole square equal to a square plus b square there। Why they are doing so?
Yeah, so let's see what the 2 times thing is. Yeah, this is non-trivial, but let's do this. 1 sec. So what's happening here? What will happen? So a plus b whole square is a square plus b square plus what is the 2ab term? 2ab term will be 2 times summation of I equals to 1 to m xi minus mu m and mu m minus mu. Okay. You are writing it, right?
I know, sir. I that calculation I have.
Okay, you have. Okay. So now mu m minus mu is a constant.
Yes, sir.
Got it. So that can go outside the summation.
It can go.
So we have what? 2 mu m minus mu, and then we have summation I of 1 to m xi minus mu m.
Yes, sir.
Now, what is mu m? Mu m is summation I equals to 1 to m xi. So you have to now do the algebra and convince yourself that this is equal to 0. Forget the constant. 2 mu m minus mu ko bhul jao. Forget it. Okay. What is remaining is nothing but 0. So how do you do that? You have summation. So let's carefully convince you. Okay. So summation I equals to 1 to m xi minus mu m. You break the summation into 2 parts. What do you get? The first part is summation I equals to 1 to m xi plus, minus summation I equals to 1 to m mu m. Okay. What is summation I equals to 1 to m mu m?
Listen, I equal to 1 to m.
Mu m.
It will be summation of xi.
No. That's because you are saying it will be 0. But mu m is a constant, right?
Okay.
Mu m is a constant, you know. That's the expectation is a constant. So if I added m times, that will be m times the constant.
Yes.
Okay. So summation I equals to 1 to m mu m is m times mu m. Okay.
Yes.
Are you convinced?
Yes, yes.
Okay. Now look at the formula above. What is m times mu m?
I equal to what? Summation of xi.
Perfect. So now you have summation of xi minus summation of xi.
Yes, sir.
Right? Which means 0.
0.
So 2ab terms is equal to 0. Right?
Okay. Yes.
So baki to I think is clear.
It's clear. Therefore, I could want to xi minus mu m whole square less than equal to xi minus. अच्छा mu m को xi कर दे, m into mu m करके. This one, sir? Yeah.
So basically वो change कर दिया. So basically mu m minus, so what do you have? You have summation I equals to 1 to m xi minus mu whole square equals to summation I equals to 1 to m xi minus mu m whole square plus mu m minus mu whole square, right?
Yes, yes.
Now mu m is a constant. Mu is a constant, right? So mu m minus mu is a non-zero value and square is always positive. So wahan se can you convince yourself that the inequality comes? If a square, so let's say the first left hand, okay, so let me highlight it. So let's say this term is a, okay, and this term is b, and this term is c, okay. C is a constant greater than 0. So a equals to b plus c, Therefore, and since b plus c is a constant greater than 0, that means a always has to be greater than b.
Yes, sir.
A equals to b plus, let's say 4, then a is greater than b, right? So वही बता रहा है. So x minus mu is a is greater than equal to b, because this is a non-zero constant value.
Okay, okay.
Square is always positive.
Clear.
Okay. So this is a interesting and difficult question. There's
It
somewhat.
was okay, sir. Not that difficult.
Hmm.
Third question. अच्छा, third तो मुझे पता है. छोड़ दीजिए sir. Fifth. Sir, ये question मैंने I have solved it. Okay. This one. The answer is wrong. This answer is wrong.
2 squared 10.
This question is wrong. Answer is wrong. I'm telling you the formula also.
Okay. So one formula is very obvious, which is wait, let me read it a bit carefully. So let's say my point is a comma b. Okay. So basically my point a comma b is the point where okay. So we have b plus 4 by a plus 2 equals to 3. So do you have this as?
I have solved it, sir. Let me see, sir. I'm telling you. This is week 2 or week 1? This one?
This is week 1.
Week 1? Achha. Formula I got it. I'm telling you the formula. Yeah, formula is t equal to determinant of ax1 plus dy1 plus c upon root over a square plus b square. Okay, sir.
No, you don't know. So that you don't need those things. I don't know what that will give you. So basically the solution can be found like this. That so you have a point -2 -4, right?
Yes.
And then you have a line which is there somewhere on the right, let's say. And then you have to find the shortest point. Sorry, you have to find the perpendicular distance. So let's say that point lies on a let's say there is a point a comma b on the line fx, which is so that if you draw a line from -2 to -4 to a comma b, that is perpendicular to fx.
That is
Okay.
the shortest distance.
Yeah, that is the, so you have to identify a comma b, right?
Yes.
So what can we tell about a comma b? First of all, the slope. So if two lines are perpendicular, then their slopes can be multiplied to get -1. Okay. Now what is the slope of this line? -1/3. So therefore, the line joining -2 and -4 and a comma b has slope 3. Right? That you agree, okay? So what is the line joining a comma b and -2 -4? That is b plus 4 by a plus 2. That is the slope.
B plus 4.
So basically b minus -4 by a minus -2. So we have a comma b and we have -2 comma -4. How do we compute the slope given 2 points of a line?
y2 minus y1 upon x2 minus x.
Exactly. So that is giving us b plus 4 by a plus 2 equals to 3.
Yes, sir.
Agreed?
3 not, sir. 1 minus 1.
No, it's perpendicular to fx.
Okay, in that way.
So m1 m2 equals to 1. So if this is -1/3, the other needs to be 3. Then the product will be -1. Sorry, m1 m2 equals to -1.
Yes.
Right. So the slope of a comma b and -2 -4 will be 3, and that gives you one equation.
Yes.
And the other equation you are, so can you write it out quickly? It will take a minute maybe.
3a plus 6 equal to b plus 4. Or 3a plus b equal to -2. 3a plus b equal to -2.
No, 3a, you just told me 3a plus 6 equals to b plus 4. So how can it be 3a plus b?
3a minus b.
Okay, yeah. So 3a minus b equals to -2. That's one equation.
Yes.
The other equation you get from putting it in the line, a comma b lies on this function.
Okay.
So what will that give you?
Y equal to b. And b equal to -1/3 a plus 2. Or 3b equal to minus 8 plus 3a. Or 3 minus 3b. 1 6 I'm doing it. It was it is 2 na? 2. Which is 6. So, plus 6. So down 3 a plus 3b. A plus 3b equal to 6.
So basically you have minus 1 by 3a plus 2 equals to b, right?
Yes, sir.
So you have to take 3 common. So you have 3b on the right hand side and you have minus a plus 6 equals to 3b.
Yes, sir.
So what do you get? A plus 3b equals to 6, right?
3a minus b equal to minus 2.
Yeah, so these calculations have to be done quite carefully. But now given those two equations, a plus 3b equals to 6 and whatever we got earlier, minus 2 wala, this should give you the answer. Can you quickly check?
That's okay, I'm doing it. Equal to 2.
B equals to 2, okay.
B equal to 2, so minus 2. Plus. So A equal to 0.
Okay, A0 and B2, then what does the equation distance come up to? A0, B2 versus minus 2, minus 4. What is the distance?
0 2, comma, minus 2, minus 4. Root over 0 plus 2 whole square. And 4 plus this 2 plus 4 is 6.
Yeah, so 2 square plus 6 square. Yeah.
40. Root over 40. Equal to 5. 2 root 5.
2 root 5, no. Root over 40 is what? 4 into 10.
10 into 4. 10 into 4. 2 root 10. 2 root 10. Answer is there. Take it, 5.
Okay.
It's done. Now assignment 2, sir.
Okay, assignment.
2, 3, 4.
2,
3, 4, 5. Assignment 2.
Lot of them. Let's see.
Yeah, lots of questions, but I will do it fast. I will try.
Let's see whether I remember these things or not. Okay. So which one?
The second Bloom filter.
Okay, Bloom filter question. Suppose Bloom filter is constructed with 3 hash functions that the bit vector is this. For a query element X, if hash values of H1 equals to 6, so H2 equals to 2 and H3 equals to 5. Okay, so H1 is 6. So 2, 5 and 6, right?
Yes, sir.
So okay, so the counting starts from 1.
The 2, 5, 6 मतलब होते हैं. 2, 5, 6 मतलब second, 5th और 6th में 1, 1, 1 लगा देंगे.
Yeah, so this is 2, right?
Yes.
So 2 is 1, okay?
2 is 1.
So no, so what does Bloom filter do? It just queries the okay, so oh sorry, my laptop is about to be switched off. Let me just okay, fine. So okay, so यहाँ पे question में first the important thing which is mentioned is 1 based indexing. What does that mean? We start counting from 1. Okay.
Yes, sir. Yes, sir.
So in the bit vector, first position 1 is 0.
Yes, sir.
Position 2 is 1. Okay.
Yes.
So H2x will get 1.
H2x.
So H2x basically looks at position 2. That's what a Bloom filter does, right?
What's it? Can you write H2x equal to 2?
Okay, so what does a Bloom filter do? X is a bit vector. Okay. H1x, H2x, H3x are all hash functions.
Fine, sir.
Now equal to what? Equal to position. So each of the hash functions is specifying a position where it will check whether the bit is set or not. Okay. So H1x checks at the 6th position.
Okay.
Right? H2x checks at the second position, H3x checks at the fifth position.
Yes, sir.
Okay.
Yes.
So now in this bit, X bit vector, the second position, the sixth position is 1. Can you quickly count and confirm?
0, 1, 2, 3.
No, one based indexing. Remember question.
1, 2, 3,
That's very
1,
important.
4, 5, 6, 7, 8. Matlab it's sixth position is 1, sir.
Sixth position is 1, second position is 1,
Yes, sir.
and fifth position is
1.
okay. So very important, one based indexing. Otherwise, the answer would change. Okay.
Okay.
So since the Bloom filter is seeing that all three of the position it's checking has one bit, then in general, what does it mean? That X may be present there
Or may not.
or may not. Why may not? Because other numbers could have set these positions.
Yes, sir.
Right? Okay.
Yes, sir. It's clear.
Hmm.
Then, sir, X may be present in the group. Take it.
Yeah.
Clear.
So that's it. Yeah.
Sir.
So the very important, I'm telling this one based indexing, because if you were counting from 0, like you started, then one of these would have become 0.
Yes, sir.
And then X is definitely not present.
Yes, sir.
Right? Then the answer would change. So be careful about that.
Okay.
Hmm.
Then the third question.
Okay.
Third, fourth, fifth. This one.
I see. It's a rather big one. Let's see. Consider the Bloom filter implementation. S1, S2 is the universe. There's M bits. And there are K independent hash functions, which maps the elements to 0 to M minus 1. We assume that each of the hash function maps each element in the universe to a random number uniform in 0 to M minus 1. For each S, we set to 1 all of the bits BHIS is equal to I is equal to 1 to K. So for all the hash functions H1 to HK, for each input S, it is setting the corresponding bits to 1. That's what we discussed right now, right?
Okay.
Each of the hash functions refers to a position which is given by HI of S, and that position on the bit array is being set to 1. Okay. The setup is clear. So which of the following statements are true as you increase K, the number of hash functions, right? So is the setup clear in your mind?
Setup is clear.
Okay. So there exists a value K0 such that until K reaches K0, increasing K actually decreases the probability of false positive. So there exists a value K0 such that until K reaches K0, increasing K actually decreases the value of false positive. So what it's saying is, let's say we have few number of hash functions, which is like K less than K0, that many hash functions, we have few of them. And now if we increase the number of hash functions, then that reduces the probability of false positive. Okay, why? Because let's say you had only one hash function, right?
Yes, sir. Yes, sir.
Then it's set a bit, it's basically setting a bit to some position, and then it's checking later on whether so basically it's only setting one bit if you have only one hash function, right?
Okay.
And then some other number comes and that's only setting one bit, and if the same bit matches, then there's a false positive. Because the second number was not actually inserted into the Bloom filter, but it will still give positive. Okay.
Okay.
Now, if you have two hash functions, then there are two places where these two have to match.
Okay.
So maybe I'm not clear. So let's say you insert number A. Okay. And that marks only one position as 1 because there is only one hash function, right? So A has been inserted into the Bloom filter. Let's say it that way. Now B has not been inserted into the Bloom filter. But let's say B also sets that same position as A to 1. Okay. So then B is a false positive because even though B has not been inserted, it will still get 1. So that is for only one hash function, right?
Sir, I understood the question. I have gone through the explanation and now I understood.
Okay.
The thing you only told me. Now I have matched that to I got it. Understood.
I see. So basically, if you increase the number of hash functions, then there have to be more matches, and that is low probability.
More false positive also.
Less chance of false positive, because instead of matching at only one location, it now has to match to 2 locations.
Yes.
Or let's say 3. So that is less likely to happen.
Yes, understood.
Okay.
And next question is fifth.
Fifth.
Sir, fourth one.
Fourth. Okay. Let's say you have designed a Bloom filter using an array of size m. Suppose you only used m hash functions, that is k equals to m. What is likely to happen? Okay, the false negative will still be 0. So what is this? The false positive rate will be very high. I see. So you have m entries, okay, m entries in the bit array.
Okay.
And you have the same number of hash functions, okay? So if you have that many hash functions, so let's say the hash functions are all random. That's our default assumption and default requirement. Hash functions are random. If there are m hash functions and then they randomly choose m positions, then even if we insert only one element, all the m positions will be set to 1 randomly. Is that convincing?
Convincing.
Okay. So if you have only one insertion and all bits are set to 1, then the number of false positives is very high, right? Because any number that comes after that, it will say that yes, it is inside the Bloom filter. So that many hash functions is not good for that many bits. So that's what it's saying here also.
But it's clear. But the false negative is still be 0 because so high the false positive rate will be that it will tend to be 0. That false negative.
So false positive. So you can ignore this first line. Maybe it's not useful. The false positive will be very high. It will be very high because even if we insert one element, all the bits get turned on. Why? Because there are as many hash functions as there are bits.
Yes.
Right.
Yes. Good. Clear. Fifth one.
Let's assume we have a hash function which maps m unique keys into an array A of length n. Okay. M unique keys. Okay. Into an array of length n. In this, we have each key mapped independently and uniformly to any of the random slots. So there are n random slots, which is the array A, and we have m keys, which are mapped uniformly and randomly. So what is the average number of keys that are mapped to the first slot? So average is again synonymous to expected.
Same.
So you have, what do you call? Sorry, you have m keys that are mapped to n slots. So what is the probability of an item going to any one slot? That is 1 by n. That is correct, right?
For m by n.
Yeah, for m objects, there is m by n.
Okay.
That's it.
Sixth one, sir.
Suppose there are two different sets S and T. Using the same k hash functions, we create separate Bloom filters BS and BT for S and T. Then we compute a new bit vector by doing bitwise and. Okay, sorry. Okay. There are two different sets S and T. Using the same k hash function, we create separate Bloom filters for S and T. Then we compute a new bit vector B by doing an AND of BS and BT. What can we say about bit vector B? Okay. So the setup is clear. So we have two sets. We have two, let's say we have two items S and T, and using the same hash functions, we create two Bloom filters. Bloom filters meaning we have. Yeah. So basically, since we are taking AND B, so if we are taking B AND of BS and BT, that means any position which has 1 in BS and BT will have 1 in B, right?
Yes, sir.
Because we are taking AND. So also note that we are using the same k hash functions. right? So the same hash functions are setting those corresponding entries of BS and BT to 1. So that gives us 1 here. So basically, if you, so again, recap of Bloom filter, we have k hash functions, each of them identifies a position, right? And sets it to 1. Okay. That's what Bloom filter does. Okay. So we have k hash functions that operate on these two sets and set the corresponding entries to 1. Okay. So remember that the hash functions map to a position, right? So if that position which hash function maps to is set to 1 in both cases, then in B also it will be mapped to 1, right? Right. So therefore, then B will also be a Bloom filter for S and T. Because if any item is there both in S and T, then the same function will apply on those common items to S and T, and then it will set the same positions to 1. And then if you do AND, then this position will also be 1.
Yes, yes, yes.
Right.
Sir,
So the distinction here is basically intersection versus union. That is the key. And yeah. So AND corresponds to intersection. That's the key concept. Okay.
Sir, आप बाकी questions कैसे करेंगे sir?
Yeah, that's what I'm thinking. How many are there?
1, 2. Count fields के थोड़ा algo के बारे में पूछूंगा और ये सारे ये अचानक बहुत हो जाता है.
So what is here? Assignment 2 mein, what else do you have?
Assignment to finish.
Oh, assignment 2 is finished. Let's move on. Just let's see what else is there. Assignment 2 is finished. Okay. So
Yes.
3 you said. That's happening.
Actually, sir, you explained to me, but it was not convincing. I didn't get convinced.
Which part?
Sir, I'm telling you the question number. Okay, questions. After 1 and 3.
1 and
First and third.
oh, 1 I remember I explaining. So K shingles things, why are you not convinced?
Sir, these many elements are there.
So shingles is what? Shingles are any K shingles are any K consecutive items that occur in the string, right?
Sir, can I write this statement?
Sure. I mean, it's not a very clever statement, but okay. So K shingles are any of the K consecutive strings or characters that appear in any string. K consecutive characters appearing in any string at whatever starting position, does not matter. Okay. So K shingle means that it has to be K consecutive characters from the string. Okay.
Starting point can be anything.
Starting point can be anything. Okay. So K equals to 4. That means we are looking at 4 consecutive characters from the string. Right. So there will be D, how many ever there are in D. Okay. So why were you not convinced last time? I'm not sure.
Earlier, sir, I was thinking permutation combination of things.
No, there is no permutation happening here. It's just sequentially counting the number of characters. For any two sets where H comes from the family of min-hash functions, it is possible to construct a example so that the probability that HS is SJ is different from. So this comes directly from the definition of min-hash. So min-hash mein what we do, we are applying a global. So we have a set of universe, right?
Yes.
And some subset of the universe occurs in SI and some subset of the universe occurs in SJ, right?
Yes, sir. Yes.
Now we apply a permutation on the universal elements that reorders the universe in some sequence.
Yes.
And that also affects the elements in SI and SJ. So some global permutation is there which applies to the universe. And since the elements of the universe are reordered, accordingly the elements in SI and SJ are reordered. Okay. Now, if there is some element common to SI and SJ, so what does min-hash do? Under that reordering, it checks the first element of SI and first element of SJ.
Yes, sir.
So what is the probability that SI and SJ under that under that global reordering, what is the probability that Si and Sj will have the same element? That is equality. So equality is what? Under that global permutation, Si and Sj have the same first element, and that is equal to this, because how many ever common elements they have, intersection, that divided by the union, the total number of elements, gives us the probability. Right. So this is basically, this comes from the definition. Yeah.
ये तो हो गया सर. काउंट मीन स्केच एल्गो ये क्या है, थोड़ा सा बताइए, हम क्लियर नहीं हो.
Count means sketch.
ये क्वेश्चन नहीं है, ये मैंने ऐसे ही क्वेश्चन है.
So it's very so it's best to look at the video, but did you not look at the video? There's a very, very beautiful example.
Sir, it was not clear.
Okay, let me.
अच्छा, YouTube में कोई वीडियो देख लो, काउंट मीन स्केच की.
No, not count mean sketch. Professor Anirban's course. Scalable data science. Okay. So I will just point you to that, and maybe we will quickly just discuss it.
Okay.
Okay. So let's see where counts mean sketch is. I think this, yeah, lecture 11. Okay. Lecture 11 is there in NPTEL. Okay. So I am going to mute this and just take you to the relevant part, because it's the best possible explanation there is.
Okay.
So this is count mean sketch. Okay.
Okay.
So for easiest understanding, I suggest you go through this part. One sec. This real world example that he is trying on. So here, so in count mean sketch, you have these many hash functions. So here they have shown 2. You can have any k, h1 to hk you can have. Okay. Now what are those hash functions? So you have as many rows as many hash functions there are, right? And you have a certain number of columns. Okay. So like we had a bit vector in Bloom filter, target position, right? Each of the hash functions was identifying a position, right? So you could think like in the Bloom filter, H1 identifies a position amongst 1, 2, and 3, right?
Yes.
So in what do you call, contrast to Bloom filter, each of the hash functions has their own bit index. So in Bloom filter, there was only one position array. Here, each of the H1, H2 have their own position array. Okay. And here on the right hand side, this table is telling you the hash function behavior. So H1, whenever it is encountering a blue ball, it's mapping it to the second position. It's setting the second position to 1. So whenever in the input data it sees a blue ball, it sets this to 1, this location. Okay. This is again very similar to Bloom, right? So H2, whenever it sees a blue ball, it sets this position, H2 corresponding first position to 1, right? And then it has a behavior defined for each of the possible input balls. And now, till now it's clear, right? Okay, so now it will go through one of these, each of these inputs one by one, and it will fill up this table. Okay. So if we skip a bit ahead, you see the prof filling up the table. So it sees a red ball. Red means H1 maps to first position. So here there's a mark, and H2 maps to 3 position. So here there is a mark, right? So red and then blue gives position 2 a mark and position 1 a mark. So he explains all this. So he is going by these balls one after the other. And after going through all the balls, there is a count in each of the position, right?
Okay, sir.
Are you getting till now? The procedure? Okay. And then so let's go back to the algo. This is the practical demonstration. Let's look at the algo slide. So here, what bit said? We had 2 hash functions. Here there are k hash functions, right? So w hash functions, sorry, right? And we have the A 2D matrix where the rows are the hash functions and the columns are the D bit positions, right? For each of the I in W, for each of the hash functions, H1 to HW, we are setting HIX, I to we are increasing the counter to C. So C is 1, let's say, every time,
That's last.
right? We are increasing the counter. And then when we are checking whether, what's the, for Q, we are checking the count, then we are returning the min across all this. So min is what? So for each for each hash function, you have a row and a position, right?
Yes, sir.
For each hash function, you have a row and a position.
Yes, sir. Correct.
You are just taking the min in all those positions.
Okay.
So for example, here, the red maps to H11 and H23, okay? So H11 is this, H23 is this, got it? And the min of these two is whatever it is. So this is 5 and this is 6, I think.
Oh,
So it will return that. So each
Fine.
hash function and each position will give you a cell, and then you have to take the min.
okay, okay.
So you have access to this video, I hope.
I'll go again, sir.
So lecture 11, I suggest you you just view this, I think 10 minutes of video,
Yes,
and
sir,
this
sir.
is very clear.
Yes, sir.
Okay.
I'll do it, sir. Yes, sir.
I think this is the best resource I have seen. You can
Okay,
understand.
I'll do this thing.
Okay.
Sir, and assignment 4, sir. ये थोड़ा सा mathematically है, sir.
Assignment 4. Okay. Let's see. Yeah, it's a bit. So which question should we discuss? Let's see.
Sir, it's maximum, sir. 1, 2, 3. I'm telling you. There are 80% questions from here. 90%. 1, 2, 3, 4, 3, 5, 6, 7, 8, 9, 10, 11, 12. Sir, sir, can you do one thing?
Hmm.
Request. Today I will solve this question, sir. थोड़ा सा और अच्छे से करके और कुछ जो क्वेश्चन यदि एक आधा कम हुआ तो करूंगा नहीं तो कल थोड़ा सा करूंगा सर half an hour for half an hour I need it.
Okay, so you tell me the syllabus for tomorrow beforehand. Assignment 4, a bunch of questions, and then
And then sir छोटे मोटे यदि कुछ हो तो मैं I will give you the mail.
no. So you try to tell me now if you have anything else. Anything from assignment 5?
No, sir.
No, right? Assignment 5 was, I think, a programming solution.
That I know. Assignment 5 is very easy for me. I did it.
Okay, assignment
8 I have a problem. Few questions. One question, only one question. Assignment 8.
in assignment
8.
8, what is the thing? So sorry, I have only solution till assignment 7. Which one?
I solved it. Sir, please bring out. I'll tell you that.
This one. Okay.
Sir, first question, please. Sir, P and Q are convex. Then QH plus QS the whole square is also convex. I said true, but it's also true, sir.
Let me think of an example. So I think let me check once.
Yes, sir, please.
So if two functions are convex, then their sum is convex. That is right. Let me see about the square. Okay, I think I see the trick. So basically, the sum of two convex numbers is convex, that is true.
Yes.
But the square of a convex function will be convex only when it is greater than 0, only when it is positive.
Are you sure, sir?
Yeah, I think you can search online also. There's a proof that the square of a convex non-negative function is convex, but not if it is negative.
But sir, negative होने से भी kx plus q whole square होगा तो positive ही होंगे ना?
नहीं, positive हो जाएगा, but convexity will not be maintained. So one second, this one becomes 1. Yeah, so let's say you can visualize this. So let's say you have a convex function which lies below the x-axis, right? Okay, that means what? So let's say at x equals to 0, it is, so let's say it's a U-shaped curve which lies below the x-axis. Okay, now if you take a square of that, it will become positive, but the U will become a cup. I mean, it will get flipped.
If I square it.
Yeah. So basically, a convex function looks like a U, let's say. Okay.
Yes, sir.
And if it lies below x-axis, then if you square it, then what does it become? Does it remain a U or does it become a flipped thing?
It will be a mountain.
It will be a mountain. That's the thing. Mountain is not convex, it's concave. So the square is convex only when it is greater than 0.
Okay.
That is the trick. Okay.
Okay, okay. And last question, okay, last one question. Last one, नहीं उससे थोड़ा ऊपर, 9 one, ये one.
Okay, so I have to go through k-means plus plus. I'm not yet sure what that is.
Last time also मैंने आपको दिखाया था वो.
Yeah, I remember it now. Yes, we forgot to discuss in the last class. Okay, so I'll try to go through k-means plus plus once quickly. And what else is there? Can you tell me? Rest is fine, right? Okay, so this k-means plus plus question, and you are saying some question from
Assignment 4.
Where is assignment 4? This one? No, this is forwarded. Assignment 4.
Yes, sir. I found it difficult, sir.
So this one is, you have to study the slides a bit. So this one is from the slides directly, I remember. So for space saving sketch, if k is 1 and stream length is m, what should be the frequency of item to be guaranteed? So this one is very easy. Okay, so you remember that Moore's sorting algorithm?
What's the sorting?
Huh?
Moore's sorting.
Moore's algorithm, Moore's. Yeah.
बहुत पहले पढ़ा था ये अभी.
That's also described in the lecture, by the way, in the lecture with Misra, Gray, Scratch. So there is a lecture with Misra, Gray, Scratch. This one, lecture 10. Okay.
अच्छा.
This one you can see on the screen.
Yes, I can see.
So make a note of it. So there we also covered the Moore's sorting algorithm, which is like a basic version of Misra, Gray. Okay, MG Sketch. So what is Moore's sorting? Moore's sorting, you remember that there is a counter, single counter, and every time you encounter an element, you increase it by +1, the same element, and every time you encounter a different element, you reduce it by -1.
Yes, sir.
So if
yes, sir. Yes, sir, I did it earlier.
yeah, so if some element occurs more than m/2 times, then that will be at the end, that will be saved at the end, because that is the majority element. And since it occurs more than m/2 times, the rest of the elements which occur less than m/2 times are not enough to cancel it out.
Okay.
Right? So that's why with k equals to 1, which means there is only a single counter, then what should be the frequency to guarantee it will be at the end? It should be greater than half.
Okay.
So that is, so I think you should, so before solving this, let's see what the other questions.
I'll go through the lecture today, sir. Okay,
Yeah.
sir. And I'll solve.
So Misra Gray, very carefully you go through. Okay. And then the count min sketch, I told the lecture 10, lecture 11. Very carefully. And then I think.
Sir, today let me go. And tomorrow I will be asking from assignment 4 only. Oh, Question will be decreased, but I'll solve it.
Assignment 4. So see the rest of the part, just to like save you some time maybe. So this part is just implementation, right? Here you shouldn't have doubts.
Yes, sir.
So in the later part, where they are saying like by implementation, it is this. Those are simple stuff. Those you won't be asked in the exam.
Would be asked in the exam, sir. This thing.
So these are just by implementation. That means you have to write code, right?
11th question will come.
How it will come?
Yeah, intuition.
No. So why can you not do it on pen and paper? That's my question.
Sir, 11th आपने कैसे करूँ सर? मुझे समझ ही नहीं आ रही.
Okay, so let's discuss it tomorrow. Fine. So this will not. These are like. So this is a MD5 hash. It basically takes any string and maps it to an integer.
I have the message address.
Yeah. So you need a code to do that. How can someone expect you to do this on pen and paper?
Okay.
So why will it come? Why is your intuition telling you that this will come?
Sir, इस तरह question कुछ ना कुछ आ ही जाते हैं, I think.
Okay, we can discuss it, but okay. But I would suggest that you carefully watch the Misra Grace and that thing, Countman videos before attempting this assignment. Okay.
And sir, please tomorrow suggest some important topics that is important.
Oh, I have no idea. I am just TA for this semester, and the questions are set by the prof separately. They will not tell me.
ठीक है sir, कोई बात नहीं, that I will do it.
Okay. No, but the amount of preparation you have, you will do well. I am stopping the recording for now.